Hello, good evening. This is October 28, 2025, and we are on the another session of the OPIS3 and MWU course. This session probably last part of the OPIS 3. We're dealing with the lab 9, and we just go glance over whatever we learn. I share it with you the material that we had, and then we'll see what we can do on the remaining of the task that we have it on this activity in here. Let me share it with you. Here, let we go right now. This is MWU. Okay. Do you see my screen on the web sign?
Yes.
Okay, good. And the web assign lab 9, I just glance over quickly whatever we learn. On here, our work is that we get the Hubble constant and the material that we needed for the curve that they know as a Hubble law curve, that expansion of the universe and kind of after Big Bang explosion of the space. And then we did some kind of graph that shows how this shows that the distance between any galaxies on the universe compared to each other make it bigger and bigger. And this is a very good intuitive picture that is provided here before the recombination and after the recombination. Recombination is the one time that the particles are very close to each other, that because of that density that we have on the beginning of the universe after the Big Bang, we cannot see any light. And after 380 years, that is, they call it after the Big Bang, we have a kind of first temperature and gas transition emission light is available, and we call it this one recombination. Therefore, at the beginning, they are very close to each other, and after they get apart from each other, they can easily propagate the lights and wavelengths of the energy that we can see it after recombination. But before that, they just make it disappear based on the condenser and the diverse matter that we have. And we mentioned the history of the development. This is the first discovery by accident happened for cosmic wave background by Arno Penzias and Robert Wilson in 1964. 1992, and with Kobe spacecraft, get another data. And this data is showing all this. This is a picture of the whole universe. And you see the distribution or become more uniform and better, and it shows that in every direction of the universe you look through it, you see this microwave cosmic microwave background is there, and that shows that if you enlarge it, how big and small items you can differentiate how the chunk of the red light here is, for example, cosmic wavelength is that on radio waves. There is no color, but this is the color we assign it to them to identify where the energy is higher, for example, on the red location, and whereas the energy is lower on the blue region that we see it. And based on that, we get some provision how to calculate the each node is the Hubble main parameters on the consideration, and we just remove the distance, and all of them is based on the T prime or T we consider based on the units of the measurement of the expansion. And this is another example. We show it that because nothing can go beyond the speed of the light. All the graphs are started with 45 angle here. You cannot see any on this direction can go because that is going to be speed more than the speed of the light. This is impossible because of the special theory of Einstein. And we get some intuitive way to get the data for the SkyNet, we get the 21 centimeter on and off spectroscopy. And this one, we're going to show it quickly in here on the next part, what we did it on the last time. And then one question, we had some possible target value. Any of you guys able to take a picture of those? This one that we asked last week. Any of you guys able to complete?
I have not taken those measurements yet.
Not yet. Okay, no problem. Therefore, this is one of the key things that you can do it later on, but make sure that you put in your schedule to complete it. And we just inform it how we can do that here for the radio astronomy. For example, you specify one of them. For example, we did it M82 in here. And when we identify on a SkyNet, let me go SkyNet. For example, in here, you go to the radio observation, add new observation, you say M82. When you say M82, brings you the M82 location. You don't see it here, you see it by this circle with the plus dot in the middle. And you compare it with the sun to see if it is how much difference. If you go further, sun gonna be shown by the red, big red dot. You see the sun is here. Find it after you move it hours, sun is here. And this object that we're gonna observe is far away. We said we're gonna have minimum separation of the 10 degree. And remember, each line that you had here, between each line is 10 degree. If it is, for example, when you look at M82 here, there's almost about 80 degree or more distance between the sun. Therefore, this is a good target at this place that you can measure. You can assign your measurement like M82 uh, um, cosmic wave background, and this is on and off. I would say call it like this. I will call it my name, for example, I am. And then what you do on the class, you just specify specifically in here. Make sure that your name that is assigned is specific, 10-degree separation from sun, and you can identify it based on different objects. If you took some of the object, for example, in here on the table, at it, you see it, you have 5 targets. You don't need it to 5, all of the 5, because this is almost, if you do observation, it's going to be taking about 120 credit from your available credit. Therefore, you choose one of them that is probably is a good chance that you can measure it. 82, as you see it in here, is about very far away, and that's probably a good chance. If you come here and check another one, M74 is very close to the sun, for example, summer here. Therefore, don't do that because that's going to be, although you specify here 10, it's gonna, SkyNet gonna take you 120 credit out, and at the end they said canceled, it's not succeeded. Therefore, that's gonna be disappear. Therefore, the another thing you're gonna check to see how many hours observable time you have. As you see it here, you have almost many hours available for the radio observation on the Greenback Observatory, and that's good. And you go to the save and continue. On the next step, you're gonna come here. This is very different than the one that we have before. On the pad type on the SkyNet that you had, first you have to identify high resolution. When you do the high resolution, it automatically check the center frequency and secondary frequency to match with this 21 centimeter cosmic background, and channel gonna be 1024. Those not to be changed. Only you have to change you make it high resolution, like the one that describe it here, high resolution mode, and you don't change any other things. And you come to the save and continue to the next page. Here on the next page, on the next page, you go specify path type. Path type is a way that record the radiograph on the Astro SkyNet. Here you have track used on the previous labs, lab 7 and 8. Here on the lab 9, you're going to take on and off. Therefore, the only difference is that instead of the track, you take on and off. And then when you take on and off, you have to provide duration 60 and right ascension and declination offset 2 and 0. Therefore, you just come here, make it 60 and 2 and 0. That's a kind of option that you're going to choose to get your observation is a better match with the one that we needed to investigate for this task. And the remaining is that repeat 0 and 0.3. Those are already available here. You don't need to change it. And therefore, the total estimated observation time will be 2 million, but because it is 60 minute duration, it's gonna be 2 times 60, it's gonna be 120 credit. Then you continue here, you double check the name that you provided, high resolution, and path track is on and off, make sure everything is right, 2 degree, 60 second duration, and total gonna be recorded here, 120 credit, and submit. Therefore, this is the task that you're gonna do to submit your observation for the SkyNet based on the actual description that is given in here, lab 9. And then after you're done this kind of SkyNet, you do observation, you just identify here which one you use it. If I use it, for example, N82, M82 is the cigar galaxy, they call it. And this is I specify here. Question? Okay. Then after that, when you get the recording, you're gonna get the, go ahead. Any question?
Here.
Do you have my voice or no?
I think it's muted.
Let me see.
Mr. Taylor, you're not coming through very clearly either.
Okay, because I forgot my headset, I think because of that, but I try to see, make it a little bit more louder, and let me see if I can make it better. How much right now is better?
I can. Are you speaking right now?
Amy?
Oh, yes, I can hear you.
That's good. Everybody is good hearing?
Mr. Taylor, I think something might have been going on with your audio.
Let me see. Yeah, it is. Everything is related. Probably, I think might be related to my audio. Let me see if I can check it. Let me see. I just
I can hear you now. I turned off my speaker somehow. I'm sorry.
let
Mr.
me
Taylor, you sound like fuzzy. I don't know how else to describe it.
I hit the wrong button somewhere. Oh,
let me check it on the. Let me stop the sharing first.
does
Let
that
me
sound
go.
does that sound better now?
Yeah, let me check audio.
I have to plug in my microphone. I've got that too. I do have one. Yeah, I thought I lost your phone there. I thought maybe yours was working on your end, but it wasn't working on my end apparently. So I'll go ahead and make a quick adjustment. This is easy. Sorry about that, everybody. Okay, can you hear me okay now?
Yeah,
It's
I
still a
hear
bit
you.
like,
But how about me? My voice is better right now?
Yes.
Okay,
Okay,
how's
very
that?
good. I just tried to set up a change. Hopefully, right now is better. Yeah.
Yeah, you sound good. Can you hear me
Okay.
okay too?
Yes,
Yeah.
you're
Yeah.
good now, Mr.
Yeah. Very
Yeah,
good.
I'm on my microphone. I'll just do that. That's a little bit better.
Okay.
Yeah.
Good. Thank you.
Sorry about that.
Thank you for always correct me if something goes wrong with the audio or video. If you don't see it, let me know. Okay, then so far that we're describing the kind of how you identify the on a SkyNet and do the observation. And then after you observe the item that you have, you're gonna have the data available on your observation. For example, in here, one of the target that we have is we have here different targets available, but you can choose it anything that you like it. For example, I use it here MO8 before, and when you look through it here, when you get the data, you click on that. Let me go from the beginning. On here, for example, you observe it, and this is archive it on and off, and then you click on that. When you click on that, it brings to you here observational data. And here you go directly to the Green Bank observational data that is saved in here. This is actually you go to the Green Bank observatory data that you have. And here there is a kind of different item available here. You can look through it. Three things is important here. There's three things that you see it here: live spectrum, and calibrated on source spectrum, and calibrated off source spectrum. And this one is described here. We can go over together how that is gonna be worked out. But before you're doing that, you will go, there is a tutorial also available then provided here. But whatever we do on here, we just calculated Z value. Z is the one redshift parameter that we said if it is less than 1 most of the time or close to 1, and sometimes we can see it more than 2 or 3 on the galaxies that is far away from us. Therefore, based on this emission, we will get live spectrum tools, measure the central frequency of the target galaxy that you have. Therefore, what you're gonna do, in this section, when you get the graph, you have to come use the live spectrum tool, measure the central frequency of your target galaxy emission line to 0.1 megahertz. And therefore, you're gonna come here, and you go to the live spectrum. Oh, okay. In the live spectrum that you have, the central emission that you have is about you will see it here, is about 1420. Why it is 1420 comes? Let me go back. I describe it here. For example, if you go back in here, you see 1406 to 1421. And this one is, you see 1421 is going to be one of the central values that you have, but you cannot get it from here because this one is accuracy is very low. You can get it here probably 142, probably 21 something. But here is data is very not very accurate here. Because of that, we come to the click on the live spectrum. On the live spectrum, bring it this one very kind of enlarged in a way that you can get estimate data better than the one that you have on the previous stage. Therefore, in here, do you have a question, Ruan? You go ahead.
So is the live spectrum just a zoom in tool? Does it like process the data in any way or just zoom in?
Yeah. It is kind of zooming to make a measurement better. It means that you have a graph here, but when you click on the graph, you cannot get a very clear understanding. You see this distance between the object are not very good. But when you see the live spectrum here, on the live spectrum, you can get the data. When you click it on that, you will get the data. As you see this number here, you see, when I click on this different location, it gives me
you the reading.
Yeah, it is here. You see this one. When you're changing this one, the data and the on the down on the left is changing. Do you see?
Yes.
Okay, therefore, this is provide better measurement. This helps you out to measure the central point more accurately than the before. But here on the previous time, you cannot do that because if you click in here, only gonna zoom it. It doesn't gonna change or give you what's the number unless you guess it. It is 140, 420, one something like, but you cannot get exactly what in here. But on here, you can go and move it your cursor, and you get the actual midpoint that you needed on here and here, which one that you needed. You will get actually the number. You can only stay your cursor nearby and record and write it down on a piece of the paper. And then you go back here, you identify when you're using that equation, you put the value on here, megahertz, and then using this formula and you're dividing the, what do you call it, C over the lambda emission. And the lambda emission, we know that 21.1061, and you will get the actual megahertz of the emitted frequency. And then you divided this one versus this one, and it gives you the redshift, actual redshift level. And there is a sample equation calculation is here. If you click it, it gives you, for example, this is observed based on the live stream, and this is emission line that we know that 1420.4, and this one is actually comes here. 14, I think we had another, not here. Let me go back, close this one. We had on the lab 9 that based on the, what to call it, observed the frequency that we have, this is the value that we get it based on the formula. And this is the formula that we get it from the observation. Therefore, this one of them, this is observed, this is emission based on the formula that we calculated. Then we just put it on this Z evaluation parameter, and we get the value about Z. And therefore, this one, it helps you out to get the this percentage of error as you need it here, that you put it in here. On here, as you see it, only you needed this part that you calculated from the redshift of your target galaxy that you observe. Any question?
Regarding the telescope, why can't we just measure purely the wavelength? Are there any factors that prevent us from directly measuring the wavelength instead of first measuring the frequency?
Yeah, for example, let me go to here. This is a question that we have one observatory here. One is the related Green Bank Observatory that we're doing. And that Green Bank Observatory data after the observation, it gives you as a curve here. And then we go to the live stream to get the actual value, because when we removing the mouse on the curve, it gives you different coordinates of this curve. Can you repeat the question that hopefully I get it correctly?
Are there?
Yeah, go ahead.
I
on.
figured out the answer. I figured out the answer to my question. Thank you.
Okay, yeah, just kind of weighing in that too, just the idea that we could talk about frequency or we could talk about wavelength because they're inverse relationship through C. So talking, I think it's just a choice sometimes on which way you want to talk about, if that makes sense.
Yeah, the reason is here. For example, Z is here based on the wavelengths, is actually as you see it here. But the program on the lab 7 and 8, we use a different way, that each of the frequency we can rotate based on the speed of the light over the what to call it, frequency of the observation. And then C gonna disappear, and then everything is remaining gonna be based on the frequency of the observation. And then that frequency of the observation, we can calculate it easily based on the speed of the light over the emission wavelengths, that is based on the length parameter. And this is a kind of target that we're using for our calculation. And also here, when you're gonna get after you calculate the redshift value, then here you can provide one sample of your work, how you calculate the Z, and you put it on this box in here. The next task is going to be, this is kind of things that is given for you. For example, this targets, this is a period of the Cepheid observation. For example, this CIGAR M82 had 88.7 days of the repeating the light curve. If we go back to the this lab 6, let me go to lab 6. I want to show the graphs that we had it before to get some idea of what we are doing. And the one that is related to the Cepheids. The one that we did, probably it is, I think here they given incorrectly. It should be on the lab 5. Last time that we had the same issue. I think this is related to the plexors, Cepheids. Here, yeah. Here, the Cepheid, we have a period between the two peaks. Normally, on the Aral Rayleigh, they are very close to each other. For example, between two peaks, it's going to be around 1 or few days. But on the Cepheid is longer, sometimes several days, sometimes tens or 20 days. In here, as you see it, for example, Cigar Galaxy, there is a Cepheid, there is a variable star on the Cepheid on that galaxy that is observed about 88.7 days. It means that this peak period between them is about 88 days. Therefore, those are longer. Because of that, we can measure the apparent magnitude accordingly on the formula that we learned. And based on that, the formula is given here. If we have a period P, and if you put in this formula, you will get the magnitude accordingly, absolute magnitude. And
real
this
quick,
is
to weigh in, just I want to be careful here because we did this last spring, but I don't think you guys, did we do lesson 6 yet this fall? I don't know if you guys have seen this equation before for the Cepheid variable. It is a fancy equation. It basically Cepheid variables, they oscillate, and the rate they oscillate is actually related to their brightness. And so it's relating back to. So I don't know that we did this lesson together yet this fall. It's one that'll be upcoming.
Yeah,
Science
we're gonna do
Olympiad
that.
moment.
Yeah, exactly. We're gonna do that on lab 5 and 6. This is the kind of things that we're gonna go on deep of this equation, but neither on the lab 5 or lab 6, we don't wanna learn how to prove that or how to memorize that. We don't wanna memorize that. But this is kind of things that shows that how the Cepheids and the error Rayleigh help us to get based on the period, we get the absolute magnitude, and based on the absolute magnitude, we get the distance. We're gonna learn later on the lab 5 and 6, but on the OPIS 2. But whatever we're learning here is that we're using this formula is known, and you can get it from OPIS 5 and 6, and you just do it without knowing what this comes from. But you can back through here to learn how the distance development is happening. This is one of the key development on the early 1900 that help us to understand the size of the universe. That we're gonna go in more detail, and we're gonna actually measure a few of them in the lab 5 and 6 together. But for now, on the lab 9, this activity you can put it aside and do it after lab 5, but you can do it right now, just putting the variables on the equation, but you will learn more detail on the lab 5 and 6. Therefore, if I think this is too much mathematics and things like that, we may push it this one afterward. We learn the lab 5 and 6, then we go and complete this one later on. What do you think, John, is the best approach? Is that possible? We just put learning here for the lab 7. We just finish it up here based on the getting the z value of the
Yeah.
expansion redshift, and
Hey.
then remaining we're gonna go over the after we learn OPIS 5 and 6, we come back again on this to complete. This is not left, just few kind of formula and boxes that we're gonna complete lab 9. If everybody comfortable with that, we just push it this one for later time when we learn OPIS 5.
Yeah, I really like that a lot because a lot of times we do things so compartmentalized. Where in astronomy, everything's really related. And it's nice to do this now. And then when we get through 5 and 6, we can come back to this radio stuff, remind ourselves how it works, and see all the
Yeah,
bigger connections. Sounds
yeah,
good.
I think that might be best idea. As I feel it, there is too much formula is there, and if we
A
want to
lot.
learn that one, it's gonna take time, and you may not capture all the needed. I think
Mhm.
that might be is a good idea that we have. Therefore, we just by this way we complete the OPIS 3, except last portion that we're gonna back after we finish the OPIS 5. Lab 5. And then right now we jump over MWU. That probably you're gonna excited, but on the MWU, we're gonna have some introduction. We're not gonna go deep on that, and probably uh, next week probably we're gonna go more in depth on the MWU and how we're gonna color the moon. The first thing that we're gonna color the moon and take a picture of the moon. We'll see how we're gonna color. Although you see it black and white, but it's not completely black and white. When you take a picture and enlarge it, you see in some area grayish and some silver color. The colors on the moon is not very colorful like galaxies or nebulas or supernovas and uh, things like that, but more very close to the grayish and the silver color. Okay, let me share it with you, the MW. The one that I sent it attachment, everybody reached it. It was very big attachment, about 13 kips, 13 kilobytes. Everybody get it, the file. We don't have like a web assign on the MW because the reason is that this is not finalized yet. Probably we're gonna not only us, about 20 or 30 different university along us. We teaching the MWU and we just fine tuning this. And if, for example, any of you find something that can be done better, we may recommend to then to revise the curriculum. And finally, that curriculum may go to the web assign sometime in future. But this is the first page. I wanna glance over here to see what we're gonna do. Here, the one number that you see it here, modules that we have. This is module 1, solar system and visible and invisible wavelength. Module 2 is star clusters and HR diagram. And module 3 is the introduction to astrophotography and star birds photography. And then this is kind of module 4, probably the heart of the place that we said colorful, invisible universe. That's the one that I, beginning of this today's session, I mentioned that invisible universe, for example, radio, infrared, or ultraviolet, and the gamma ray and X-ray. Neither of them is visible. We call it invisible, but we have to color it. Why? We have to make it assignment for the intensity of the emissions on the gamma ray or radio wavelengths to see which area has more intense. Therefore, we assign it a specific color for those. And this is kind of artificial coloring. Therefore, we don't want to, in the chapter 4, this you learn how to do the artificial coloring of the different wavelengths. Mostly we're doing on the radio wavelengths on here, chapter 4. And chapter 5 is related to the white dwarf, neutron star, and black holes. And we're gonna check to see how we do polarization and ripples on the space-time, that we're gonna learn about the gravitational wave events and how we can figure it out on the observation. And item 6 is the radio Doppler imaging of the spectroscopy. And the last one is normal and active galaxies. And this is a very exciting object in the celestial sphere. But the colorful, natural, actual, visible light we're going to learn on first 3 sessions. Therefore, first 3 modules or 3 part of this MWU is mostly focused on the natural, actual color, but the remaining 4, 5, and 6, we're going to have added some future for the artificial coloring because of the many different reasons that we're going to describe. And module 1 is the one that we're going to work it out. The first section of that is moon at the optical wavelengths. We're going to see how we're going to do mosaicing or mineralogy. Mineralogy, we have to identify by the color what kind of mineral exists on the surface of the moon. And that's one of the exciting things, and you don't believe it. From how much distance we are from moon, by imagining the picture of the moon, we can find out what mineral located on the surface of the moon. And that is very exciting, from about 380,000 kilometers away, or more or less, we will get to find out on different point of the surface of the moon what kind of mineral we may have it. And the next section, we're going to do the radio wavelengths. And here, we're going to do some kind of reflection techniques or black body emissions that we're going to learn. And next one, we're going to do, might be another excitement, that we're going to go Jupiter's and the radio wavelengths, and we find out how we can identify various parameters, observation on that. And the last part, that is going to be another excitement, this is going to be planet at optical wavelengths. This is going to be colorful percentile and photographic color balance that we're going to do various techniques that at the end we're going to have, although here it says introduction to astrophotography, but actually astrophotography start from the beginning. But we're going to learn here in a complete sense. It's not as actually introduction, but it is kind of completion of the introduction to astrophotography. And hopefully we learn on those. Okay, this is kind of very overall view of the modules that we're gonna go over. John, if you think anything we can add it at the moment, or you wanna something, anybody had a question on this overall back view? There is too many slang are there, but we're gonna make sure that all these slangs are clarified with the public language and the kind of way that describe it diligently. I think one of the key comment that I have for Dan is that to make it this one is more popular public language than using very slang specific expertise terminology on here. But any question here before I stop by, then before going the next step, I'm just here to listen.
Yeah.
Just to clear, sorry, you go, Mr. Taylor.
No, I say go ahead. I was just gonna say I'm curious what you two are really interested in doing on this list. If there's anything that's in there or not in there that you're very interested in, it's a good time to chime up. But go ahead.
I'd say this is where the JS9 begins, correct?
What was that?
Is this JS9 begins?
I'm curious what programs we will use. There's a few different ones that astronomers use. And so we've been using DS9 and JS9 to stitch images together. But there's also Finder Chart, and there's MAST, and there's a lot of other resources. So I'm going to be looking through the resources myself to kind of see what we're used to using. And that's where, Ara, you've done a lot in class with this. It'd be great to hear what you think as far as, I like this better than that, and this is easier than that. So I had an experience last week where the students taught me because I was having a hard time using MAST to pull images of planets in. Savi and a couple others, actually, they put in a procedure up on the board on how to do it. So it's amazing that you folks can figure out how to do this thing, any of this stuff so well. And if there's any of this you really enjoy or want to see more of, it really is a time to ask. Is there any in there that you're not interested in or are interested? What's your feedback from YouTube about that?
I would say the things that I'm probably the most interested in is the star deaths and the colorful invisible universe. I think that those are just like really cool things to think about, and I'm really excited to learn about those.
Cool.
And also thank you. And also, Rowan, how about you?
Content looks pretty good. Will be useful for Science Olympiad.
Yeah. And also, as John mentioned, I think
Yeah.
you had some program that you're using, John. For example, on this class, we're using DS 9 and 12. Using?
GS9 and the JS9 is one that works on Chromebooks. We found it. The DS9 is much more robust.
Yeah.
That's what I was introduced with Luis at Caltech. That's what we used for images there. But I know the Ursa tools will do the same thing, and there's probably a couple others that will also make the tricolor images and help you to process them out.
Okay, very good. And also might be a good idea that when we go down the line by the end of the semester, if we can compare it to each other, and also we may they may have some features that help us to fine tune this curriculum for MWU as well. That might be helpful, and we can collect all of them together and give the feedback for Dan. I think Dan gonna be very liked to hear that, and also that gonna be very good contribution on development of the final curriculum as well. And that will be excitement for all of us.
Yes. I know I'm
Okay.
very interested in the mineralogy part of it too, that you can look at something and from its colors, you can figure out what it is. There's some
Yeah.
pretty cool stuff there. Anyways, yeah.
Okay. Let me make it a little bit larger here to see it better. Probably if you open it yourself, let me see it here larger. Okay.
Yeah. Do you two both have this multi-wave universe document?
Yeah, I think it was in the email that Abbas sent us.
I
Okay, good.
emailed it attached to the today meeting. And I did it. We developed. I think we started with John to develop this one, but so far we didn't have succeed to go further. But by this week, we're gonna go over probably along the class to make sure that fine tune. This is not the final curriculum, but we have to make sure that we address those along the line and make it better and better.
Mhm.
And here, this is kind of solar system and visible and invisible wavelengths. How are we gonna do that? We have module one, A and D, A, B, C, D. We will take advantage of the nearby bright solar object that we have. What's that? Moon. The bright, being bright is we can do a lot with them without burning through a lot of expenses, because if it's very faint, we have to spend about minutes and hours to take a picture, but telescope time. But the moon is because very close, or planet are close, we can get a very good benefit with a small credit that is assigned for us for the class for the SkyNet. That's one of the advantages we start with this one. We will then take use of the result of the image, and we learn how to use the Afterglow. This is the main kind of concept that we have. And Afterglow, we're gonna see it. I think from my point of view, Afterglow is one of the greatest tools that is created for astrophotography. Although right now on the market you see several different things like PixInsight or very different Nina or some other things. Those are the commercial, but this one, Afterglow, is an academic product, and you're gonna see how those are different. And learning tool from those is too much different than the commercial one, and uh, you will learn how you can compare it with the commercial as well as needed, or the other ones that you have it in the class DS, GS, and the others, 9, and then we will figure it out on that. Along the way, you will encounter a concept of the picking up skills will serve you throughout the MWU curriculum. That is mainly for the astrophotography. Okay, here the first task for A part of it, moon at the optical wavelengths. We have two terminology that we call it mosaicing and mineralogy. We're going to see what those terms are intended. We are going to begin with exploration of the universe with the closest object, moon, as I mentioned. It is big and bright enough, so easy to study. And the thing is that one thing we have to consider is a field of view. Field of view, the SkyNet Prompt 5 telescope in Cerro Tololo in Chile, it is kind of showing on the pink box. You see, this is a field of view. If we make a telescope toward the moon, it's only going to capture how much of the moon? This much. And that's the problem. Why? Because we cannot take a picture of the whole moon compared to entire moon. Let me, we can go over later on after we complete this one, because this is important to know that each telescope, probably one of the telescope, we have how much the size of the moon on the sky is that based on the sky degree, written a year, half a degree. You mean, if you consider entire universe around the universe as is about 360 degree, and this is half a degree, what that means? It is 1/702 of the whole entire perimeter of the sky. And in each direction you go, and you see this one is very low, it's half a degree. One of the quickest tool, you can measure it, and you can back to me later on. When you see the moon full in the sky, you just go over, stretch your hand, you just point it toward the moon by your finger. When you point it by the finger toward the moon, stretch it toward the moon underneath of your finger gonna disappear. Why? Because this finger, when you're stretching your hand, it shows how much on the sky, it covers about 1 degree. It means if it is moon is about twice the size of the one that is about 1 degree, you cannot see it because, that shows how small is the moon. That's a very simple tool. You can experiment and get connected to the sizes that we have. Because if you remember half a degree, you always may forget. But when you do like this practice, you will always learn for entire your life. And that's one of the great hands-on activities that we have. Okay, then we learned two things. The thing is that size of the field of view of the picture that is one of the telescopes can take it is this much. And the size of the entire moon circle is about half a degree. Okay, therefore, moon is very big. That's a problem compared to the telescope that we're gonna take. What we're gonna do? It spend about half a degree in the sky. Some of our telescopes are field of view are large, but most of do not because this one most of them they are very small. The one, for example, shows prompt 5 is very small. Therefore, to do that one, we learn first astrophotography slang and terminology, and that is called mosaic. What that means, we're learning that instead of taking the picture of the moon, we can do one option. We take a telescope that has a field of view is large, and take a picture of entire moon. That's one option. The other option of the astrophotography, instead of the taking moon in one picture, we're taking the picture in the mosaic. One mosaic is here, another mosaic is here, another mosaic is here. We just shift it on different place and take a different part of it, and then putting the mosaic beside each other, and then combine it all together and taking whole picture. This is kind of first technique we learn on the astrophotography that most of the astrophotography they do. If the object, for example, many of the object is very large. In the regular telescopes, you cannot measure it. Like M31. M31 is about 3 degrees, not about 0.5. It is 6 times expanded on the sky. Therefore, if you want to make it a picture by one of this telescope, it's gonna only take a middle part of the M31. We cannot take the other parts. Therefore, whatever we can do, if we can on some of the telescope, we will do it mosaic kind of astrophotography. It means that you are going the shot of the sequence of the overlapping images that stitch them together to make a single image that covers the entire wall. That's kind of this topic that we're gonna learn. Then we're gonna do this one, and we are going to learn how to do this in color. Why it is not the moon black and white? It is not. It's actually moon is not black and white. Moon has a very subtle colors dependent on mineralogy. That is the one that we're gonna learn, and that we learn how to saturate these colors to make them more noticeable, the minerals and colors. In part one of this module, we overview the basics of the how the astronomy collect the images and turn them into color pictures. And then in part two, we are going to learn how to submit this kind of observation to SkyNet. And part three, we just processing, post-processing of the astrophotography of the picture on the afterglow. And on the part four, the section D, we're gonna look through at how we can provide kind of blog and kind of expression, how this activity we do, how we can interpret what the colors and physical connection with the minerals are means. I'm gonna go briefly this one, that this module observation can be done anytime, except within a few days of the new moon. That's very important. This has to be remembered. This is why we don't use it in the new moon, because the new moon has a time that we have less no moon observable. We are just facing the unseen part of the moon. And however, the best study of the moon mineralogy, you want to see it when most of the majority of the moon is available. If it is full moon, is the best. Few days, within few days of the full moon, 1 or 2 days before or 1-2 days after. Therefore, you have to check before submitting to make sure that this is happening. And for the introductory video, there is a video that is provided here. You can open it and look through it. And this gives you some introduction. But I will go over here because we learned this one, how the telescope, different part of it exists on the OPIS1. And you will also notice that. And this is a key instrument that we have. And one of the key instruments that we're using on this MWU, this is a filter of the wheel. It has different filters, red, green, blue, and some light pollution and other filters. And behind the telescope, this light is located in here. As you see it, the filter wheel is located in somewhere here before the digital camera. And therefore, this enables the camera to take different colors together. Therefore, this is help us to get the different color of the picture. And this is one of the key things I already showed on OPIS1, that and also OPIS7 probably. If we take a picture of the red, green, and blue, we're gonna take whatever we get from the photograph is like this. You don't see it any color, but although it's color red and green and blue, but you have to assign it to them. When you assign it to them, you will get, this is the red part of it, this is green part of it, and this is the blue part of it. And when you combine it together, it comes the actual natural color. And this is the way that actually most of the photographs are working, and the scenario that we're doing for the astrophotography. And then this is kind of graphs shows that on the different wavelengths, how these filters are recording the domain of the spectroscopy. And this is kind of a way that we're gonna observe the observation in SkyNet. That I recommend you to review the material and take a notice of the videos. And hopefully for the next week, I stop here and don't go here. Next week, we're gonna go to show how to make the observation. And in this observation, I'm gonna show you completely like this. For example, we have a different telescopes. We have field of view is given, and then pixel size is given. And then we're gonna see how we can do the mosaicing, the pictures and other items on the SkyNet. And therefore, for example, in here, the grids of the mosaicing going to be 5 by 5. It means that we're going to have 5 mosaics on different scenario on the disk of the moon. For example, in here, probably we're going to go one here, one here, one here, one here, one here. It's going to be 1, 2, 3, 4, 5. And then another mosaic, we're going to cover the edges. One here, one here. Probably we may need it about 14 picture of the moon on different location. And that is, you don't need to worry about the identifying how to do that, but SkyNet has an opportunity. You can tell it to SkyNet, I want to take a picture of the moon by the scale of the mosaicing, such 4 by 4 or 5 by 5, something like that. And then SkyNet provide for you 14 or 15 or 16 image of the moon on different things. And then we want to switch it together and match it together and combine it. And we do it with the Afterglow. And you will see it on the next week how we can do that. Therefore, by now, I think we stop here. And the next week, we're going to go the most exciting part of it. This is an introduction to what the procedure going to be. On the next page, we're going to go SkyNet observation, how we can define the mosaicing the moon. And then we're going to go look through the various color mineralogy as well as the post-processing of the filters. And later on, we will see it how that's going to work it out for our activity for the first lab work on the MWU. Any question?
All right, good stuff. It's going to be a lot of fun. And we can do this together as we go through. And I think this is going to find a lot more manageable too, what we're getting into. It should make a lot of sense. And we just do what makes sense as we go forward. So I was looking at the time about a quarter after. So, but
yeah. And also remember that there is a links on the Word format that I sent it to you. You can open it and review it by the videos that is Dan provided. And we're going to complete it in different way. And you can ask a question and review it if you have some question that on the Dan's videos or video or presentation, we can debate on the next week. Thank you, everyone. I know that this time it become a little bit late. We just started late and finish it late, and hopefully we do it very good, productive next week, and we get first object with the MWU mineralogy of the color surface of the moon. Okay. Hope everyone have a good night, and see you next week.
Yep,
Have a
see you.
good day, Professor. Have a good day, Mr.
Thank
Taylor.
you.
I'll see you
Bye.
tomorrow.
Have a good day.
See you
Thank
guys.
you. I appreciate it.